In this recording, we will work through a few examples. Let's start with this conceptual question. We have two blocks that are stacked on the ground. And the question is, how many action-reaction pairs of force are present on this system? 2, 3, or 4. Okay, now let's try to figure them out. We have block A is going to push down on block B with a normal force. And there will be a reaction to that, block B pushing up on block A with a normal force. So that's one. Now the other pair. The Earth is going to pull down, the Earth is way below there, is going to pull down on block A. And A is going to pull up on the Earth. So that's another pair. Okay. Third, let's consider B. Block B is going to pull up on the Earth with the gravitational force, and the Earth is going to pull down on block B with the gravitational force. That's another pair. Okay, now we can go to another pair. The floor is going to hold block B up with a normal force, and block B is going to push down on the floor with a normal force. That's 4. Now, of course, there is A and B, they exert gravitational forces on each other, but they are too tiny, we ignore them, so that's why our answer is going to be 4. Okay. Next question. A large man and a small boy stand facing each other on frictionless ice. They put their hands together and push against each other so that they move apart. Who moves away with a higher speed? Obviously, if you have seen anything similar to this, your experience should tell you it's the small boy that's going to move away with a higher speed. Actually, the question here is missing something. I thought I had it here. No matter how long I prepare these things, there are things that end up missing. Okay, which of the two is going to experience the larger force? Okay. Which would experience the larger force? It's going to be the same. Why is it the same force? They are going to be action-reaction pair. The small boy is going to accelerate because of the force that the large man exerted on him, and the large man is going to accelerate because the force that the small boy exerted on him. These two forces are action-reaction pairs. The man exerted a force on the boy, and as a reaction, the boy exerted a force on the man. Okay, let's see. A large truck collides head-on with a small compact car. During the collision, let's read these answers. The truck exerts a greater amount of force on the car than the car exerts on the truck. That cannot be true. That's against what Newton's third law of motion says. It says that the action and reaction should be equal to each other. Okay, so that one is wrong. The car exerts a greater amount of force on the truck than the truck exerts on the car. Same reason for not accepting this. Neither exerts a force on the other. The car gets smashed because it gets on the way of the truck. Okay, of course, this is not even a good distractor. Fourth, the truck exerts a force on the car, but the car does not exert a force on the truck. You notice in a collision, both of them are going to be damaged, so that does not make any sense. And we have our fifth answer. The truck exerts the same amount of force on the car as the car exerts on the truck. That's our Newton's third law of motion. The truck is going to exert, for example, the action, and the car is going to exert the reaction, or vice versa. The action and reaction are going to be equal to each other and opposite in direction. Okay, let's take this example here. We have two objects sitting on a flat surface. One of them is 84 kilograms, while the other is 42 kilograms, twice as massive. Object A has a spring-loaded cylinder, so we have a spring here, which will be used to give a push to object B. When the cylinder is activated, both objects move. Okay. Now, which of these statements is true? Neither object exerts a force on the other. Each object exerts the same force on the other. Each object exerts a force on the other, but B exerts a larger force. Each object exerts a force on the other, but A exerts a larger force, and so on. And you know that the answer should be this. And that's again Newton's third law of motion. If A is going to exert a force on B, B is going to react with an equal force and opposite in direction. The mass is not going to matter. The forces are going to be equal. Okay. This is the question where people usually, all the previous questions are generally easy and usually people don't miss them. But when we get here, people can start getting in trouble. Consider a crate at rest. We can conclude that the downward gravitational pull of the Earth on the crate and the upward contact force of the floor, probably that's better, on it are equal and opposite because the two forces form an action-reaction pair. The net force on the car is 0, neither of the above. Now, I corrected here saying the floor instead of the Earth to avoid the confusion. I don't know how many times I used this question, but I guess it still has an error in it. Now, this is what we are talking about. A crate, that's not accelerating up or down. It's not accelerating sideways. So the forces on it are balanced. There is a gravitational pull on it. That's due to the Earth on crate. And then there is a normal force due to the floor on crate. Now, why would we say that these two forces are opposite in this case? Just because we know that these two forces are going to balance. How do we know that they are balanced? It's because we don't have acceleration along the vertical. So in other words, if the forces are balanced, the net force is 0. And there is another error here, crate. The forces cannot form an action-reaction pair because they are not of the same nature. They have to be of the same nature to form an action-reaction pair. Consider a horse pulling a buggy. Is the following statement true? The weight of the horse and the normal force exerted by the ground on the horse constitute an action pair that's always equal and opposite according to Newton's third law. Okay. Again, it's a no, because the weight of the horse and the normal force, they are forces of different nature. Remember, for action-reaction pair, they have to be of the same nature. Weight is a gravitational force, and the normal force is just a contact force. So there are two different types of forces. They cannot be action-reaction pairs. And there is another thing that cannot make them action-reaction pair. Both of these are acting on the same object. The normal force is acting on the horse, and the weight is acting on the horse. Remember, the action-reaction pairs act on different objects. For example, the reaction to the weight is acting on the Earth. The reaction to the normal is acting on the ground. They cannot be acting on the same object, in this case the horse, to be an action-reaction pair.